Welcome back friends to the next lecture of energy conservation and waste heat recovery. Today what we will do is we will continue our discussion on thermal energy storage. So, in the last class we talked about sensible energy storage and looked at pressurized water storage as an example of sensible energy storage. Okay. So, today what we will do is we will look at latent thermal energy storage. Okay. So, let me write that down. So, I will write it down as latent thermal energy storage, and as we said before, this is when energy is stored because of a change in phase. So, typically we will say let us say it is from solid to liquid. So, as we know, as a substance melts it absorbs heat and therefore, it changes to liquid, and then if we can maintain it in the liquid state, then the energy is already stored. And then after that, if you want to release that energy, we have to cool it down, so that as it solidifies it releases that energy which we can use. Okay. So, what we will do is, this is what I am trying to show here. So, this is where what we need is, we need a material, PCM is called phase change material. Okay. So, this is a class of materials which can be organic in nature, which can be inorganic in nature. So, the PCM that we are most commonly we are most familiar with, all of us, is wax. Okay. Paraffin wax, it is an alkane, and the way it works is, as you know, that if you heat the wax beyond a certain temperature it melts, and if you cool it down it solidifies, right. So, that is why when we light a candle, the wax melts when it gets heated. Okay. So, that being said, if we now let us assume that it is a wax type material and let us say we increase the temperature. So, what happens? The temperature at the beginning is going to rise because this is sensible heating, this is still in the solid state, and then at some point this temperature for this material marked in red, this temperature corresponds to its melting temperature. So, then what happens? Here the temperature does not, so and I am applying heat, that is granted. So, as I keep on applying heat, the temperature does not rise beyond this, but what happens is that enthalpy increases at a constant temperature, and why this happens is because of change of phase, and then once it has completely melted, then again as I keep heating it, it is in the liquid state, and because of sensible heating the enthalpy goes up and so does the temperature. So, this is for material A, this is for material B, all right. And let us do the vice versa. Now, I keep cooling it down and reducing the temperature, again the temperature will come down, and then we will reach a point where the temperature will not change anymore, but the enthalpy will reduce, and at this point it will give up heat, and then if we cool it further, the temperature we will see again is falling down. So, this is an ideal case, okay, where in a real case, you know, this wax will never come as just loose material, it will be encapsulated in something, etc. So, in a real case typically we do not see such a sharp rise, right. What we see is a more gradual increase like this. You still see that two phase behavior over here, the change of phase behavior, but instead of it being just a sharp rise, it is typically in this form, clear. So, it is happening over a certain finite temperature range. So, in PCM what is the function, or what is the principle on which it acts as energy storage? So, as it absorbs it melts, okay, it changes phase, the solid becomes liquid, and then it is stored, and then when we cool it down it is released and it changes its phase back, clear. So, this is the principle of operation of thermal energy storage using latent heat, all right. So, what we will do next is we are going to look at 3 examples, and the first one is going to be just an example here. Now, you can think of a lot of other variations using the same principle. So, solar, or rather I would say solar power with thermal energy storage. So, what is happening here? Now, let us look at this picture over here and try to see that where how this works. Okay. So, we will spend a little bit of time trying to understand each and every component of this. Okay. By the way, solar is just one of these, it is an example, as I said. The source of heat can be anything else, but why solar is because the energy source is available to us only during daytime and not during night, but whereas I would like to generate power throughout the day, right, maybe a little less at night, but still I would like to generate power. I cannot switch off power generation during night just because there is no sun. So, how do I do this? I need to store energy that I am getting during daytime to be used during the night. All right. So, what is happening over here? Over here, this is the solar trough, and where we are getting the solar energy from the sun. So, through this what happens is there is a circuit, there is an oil which is a working fluid in the solar loop, and that is denoted by this yellow line, okay, dark yellow, light yellow, and so on. So, let us now forget this part, both this branch and this whatever this hot salt and so on, whatever we are seeing, let us forget now. In a regular instance, what happens is this oil gets heated up by the sun. Okay. So, its temperature rises, it does not boil, by the way, its temperature rises and therefore, its enthalpy rises, then it flows through this loop and comes to the steam generator, and where it acts as a hot fluid. Okay. So, here what happens, water goes through the steam generator or the boiler, where it picks up heat from this oil and evaporates into steam or boils into steam, and this steam is fed into the steam turbine, and then the exhaust from the steam turbine is fed to the condenser, okay, and the condensing water goes to a cooling tower. This is the standard power plant that we already know. So, this is evaporator or the boiler, this is the turbine, this is condenser, this is pump, clear. Except over here, the source of heat, instead of being combustion gases from natural gas or coal, is actually this oil, hot oil, which has been heated up by solar energy, clear. So, this part of the loop is clear to you, all right. So, this oil, when it comes out of the boiler, it has given up its heat to the for boiling the water that came in and generating the steam. So, therefore, what comes out is cold oil or oil at a lower temperature, which is fed back to the solar panels, all right. So, this is how the normal generation happens. But now, if we do this only, then what happens? I am going to generate power from this turbine during day or when the sun is there, but however, I will not be able to generate power during night or during a cloudy day like it is today outside. I will not be able to generate, but that cannot work, right. So, therefore, I have to store some energy on a sunny day, so that it can be used later during a cloudy or rainy day or during night. So, that is what is done now by this circuit or these components. What happens here? What I am going to show over here is this is molten salt, hot salt. So, this is an inorganic phase change material, which beyond a certain temperature can be melted, and as it melts it stores heat, and then as it solidifies it releases heat, clear. So, let us say during daytime what happens? The hot oil from the solar panels is actually, instead of going entirely to the steam generator over here, it branches off into two streams. One of the streams go to the boiler, and the other one flows through another heat exchanger. Okay. In this heat exchanger, what happens is during daytime this salt goes through and is stored in a molten state at a high temperature, clear. And then what happens is, so what happens during the daytime, I am generating some power from the steam turbine, and I am also generating heated molten salt which is stored in this reservoir. As expected, therefore, like here, the oil that comes out of the boiler is at low temperature, and the oil that comes out of this heat exchanger during daytime is also at low temperature, and the two of them merges here, the two circuits merge here and they go back to the solar panels. So, therefore, this is how the oil circuit works during daytime. All right. Now, what happens during night? During night there is no flow from here, right. During night there is no flow from here. So, therefore, the oil actually flows in this direction, where the salt right now releases heat to the oil, clear. So, the salt starts flowing from the top container to the bottom container, and the oil moves up like this during night time or during a cloudy day. The oil will move up like this and gain heat from this heated molten salt, and then the cooled down salt will accumulate in the lower reservoir. The heated oil then will go through this circuit, go to the boiler, generate steam so that the power generation is maintained, and then come back and just complete the loop like this. Clear. So, during daytime the oil branches off into two parts, one goes to the steam generator and the other goes on to heat the salt. During night time, when I do not have solar energy, this heated salt actually heats up the oil which is fed into the boiler and which generates steam for electricity generation. Clear? All right. So, I hope this figure is clear now. It is very nicely represented, but only thing is you need to know what is happening. Clear? So, this is one example where I am using solar power with thermal energy storage. What else? This one is latent heat again, or not again, this is latent heat energy storage. This is for an air conditioning and ice formation. So, before that, see, air conditioning units, that the way we see the standalone split AC or the window AC actually has the refrigerant flowing through the evaporator coils, over which air is blown, and that is the refrigerated air or the cooled air that we get inside the room. But if you look at larger installations, for example, this academic complex that I am in right now, hotels, etc. So, there what happens is you have a large air conditioning plant, and where you actually produce chilled water, and then the chilled water is recirculated through the different rooms of that utility, and that over the chilled water pipes is where we blow the air and the air cools down. Okay. So, the evaporator units, the so called quote unquote evaporator units that we see in the rooms of this, let us say in this classroom or in the hotel rooms, etc., or in the office building, is actually not a standalone AC, and where the refrigerant is flowing through the evaporator coil, but it is actually chilled water that is flowing, and so it is a heat exchanger. Okay. So, cold water flows through a pipe and air flows over it and gets cooled. All right. So, that is what I mean by chiller unit. Okay. So, now let us look at this. We have a chiller unit, two chiller units, let us say, working in parallel, and which is producing chilled water. So, chilled water, typically what happens is it goes into the building and flows through these different building cooling coils, as they what they are calling here, which is typically the what we call the these are the evaporator, the quote unquote evaporator units that I talked about, through which chilled water flows and air flows on the outer side and it gets cooled. Okay. So, then what happens, the chilled water as it comes out of this heat exchanger or of this evaporator unit is now at a higher temperature. It comes back, is pumped again into the chiller units, where you have actually refrigerant that cools the water down. Okay. In a miniature scale, by the way, this chiller that I am talking about is the same that you see in a water cooler, except that water we directly take from the tap and drink, and in this case, in a larger case, that water actually is pumped through these plumbing lines into the rooms and where it is used for air conditioning. Clear? So, now this is an example where during the daytime, during the daytime or during when you have, let us even think about a situation where there are frequent power cuts. So, what will happen when there is a power cut these days in cities or in the office buildings, apartment buildings, we run diesel generators, diesel gensets to provide us power during power cuts. Now the cost of such energy is much higher, as we know. Diesel genset, to generate electricity out of that, the kind of expenditure, the cost of generating that electricity is almost, I think, 3 times compared to what we get from the grid. So, therefore, it is undesirable. We should try to reduce that consumption, if not eliminate it completely. So, that is also one example. Night and day is one, where during the daytime maybe we can run a chiller at a we run the chiller at full load, and at night time we do not. So, let us see, let us first look at this, how this works. So, during the daytime, let us say when I have or during during off peak hours, forget daytime actually, during off peak hours when we have higher electrical energy available to us, then what we do is we run the chiller and produce excess cooling water. So, part of that, whatever is required, goes into cooling the building during off peak cooling mode, and the rest of it goes in a thermal storage tank to generate ice. Clear? All right. So, again I repeat, what happens is when during off peak cooling mode, when I do not need so much of cooling, let us say the temperature, outside temperature is not that high, or the cooling load, not many of the rooms, if we consider an academic building or an office building, it is a weekend, let us say not too many people are working or not too many classrooms are occupied, then what happens is my building cooling load is low. So, what I will do is I do not need to feed the entire chilled water to the building, instead I will only feed partially whatever is required, and the rest will be used for generating ice. And this is one where what we can do is this ice, the water in the during the peaking time, the water directly comes to this thermal energy storage tank, where it actually loses heat to the ice, as a result of which the ice melts, and then it gets chilled and comes out and goes into the building. So, this ice can produce additional chilled fluid during peaking hours. So, there is actually a new startup called InfiCold. If you can look it up in Google, inficold.com. That company, what it is doing is, it is trying to come up with a unit similar to this, especially trying to reduce the dependence on diesel generator sets, and trying to reach out to farmers, to dairy farms, etc., where normally we lose a lot of foods, let us say vegetables, because we cannot keep it in cold storage, or in dairies we lose a lot of dairy, lot of dairy products go bad because we are unable to keep it at refrigerated temperatures. So, what they are trying to do is use something similar, or rather something as very same principle, trying to use a thermal energy storage device as a plug and play, which they at least claim that you can plug into any refrigerator, and when you have additional electricity or energy available to you, you can use it to generate ice, which can be used later, let us say during a power cut, in this manner, where the chiller is off. Now, in a power cut the chiller will be off, so use it for chilling in this manner. Clear? So, this is another example. So, let me write down as a second example, air conditioning, right. The third one is also air conditioning, but in a little different manner. So, this is building energy storage. The way it is done is, let us say the walls of the building think about it. Okay. If we can put some phase change material in the walls of the building, what will happen? Okay, that is the overall objective of this exercise. What I am showing you is actually a case study. It was done by a company, and I have Abhari, who is one of the probably the principal investigator, he published this work, and this is what I am trying to show. So, if you look at the time of the day, if you look at the load of the air conditioning load during the time of the day, what happens is, as we saw even yesterday also, what happens is the load goes up like this and comes down. So, there we talked about electricity generation required or electricity load as the day progresses. Here they are showing the air conditioning load, not it is similar, right. So, what will happen? What we are trying to say is that during some hours you will have peak loads, some intermediate loads, sometimes base loads. What he is trying, what the objective is if we use thermal energy storage, it may be possible to bring down this curve down to here. So, the electricity that is required to meet the load will be much lesser, because thermal energy storage can fill up this gap, right. So, the demand curve will come down. How is that going to help? It is going to help because you know that if you, for even residential purpose, if you look at your bill, you will see that beyond a certain point, beyond a certain units of usage, the electricity, the cost of electricity per unit goes up. There are certain slabs, right. So, if I can keep myself below the slab, then it will save me a lot of money, right, because not only it is additional electricity, but this is additional electricity at elevated rates, clear. So, this is the motivation. So, what they did was, they actually there is this building material, the outer wall, they added some PCM to the insulation. Remember, this is here, I mean the walls right now over here is not just your brick and concrete, but it will have several layers. So, it has cellulose plus PCM pellets. So, this is some kind of a phase change material that they use. So, the details of which I think they may or may not have revealed in this paper. But anyway, this is a phase change material that they have used, an organic material that I know. And what they did was, they tested it in Oak Ridge National Lab in US. Okay, it is one of the science national labs in US, very well known. So, there this testing was done. They are calling it building envelopes and passive storage, and why passive storage I will come to that when we talk about active storage, we will know. So, in this wall they actually put in some phase change material. So, what happens during night time or during colder days, what happens is the phase change material solidifies, and as it solidifies it releases heat, which is okay because it is anyway a cold day. I really do not need that, and the room temperature, therefore, even if it releases heat, the room temperature inside is still within ergonomic limits. Actually, it is good. Okay. It may be good, I will not say it is good, but it may be good, it may be more comfortable, all right. And then, or during night time, for example, when you do not in a moderate climate where the days are hot and nights are pleasant, I can choose a material, a phase change material whose melting point is typically somewhere in between what is the average day temperature and the average night temperature. So, during night the PCM solidifies, and as it solidifies it gives up the heat maybe to the outside and the inside of the room, and that keeps you warm, which is not bad. And during the daytime when the temperature goes up, it absorbs the heat and prevents it from going inside. Okay. It absorbs the heat at the wall itself and melts, and therefore, it does not go through the wall into the inside of the building. So, therefore, what happens? The air conditioning load goes down because the temperature inside the room is already reduced to certain extent. The heat flux that needs to be removed, the heat load that needs to be removed is less. So, this is what they showed, that adding PCM to the insulation actually reduced the peak heat flux by 33% and the net heat gain by 13%. Why? Because part of the heat was absorbed by the phase change material. Okay. And this was nothing, this was just the building the wall itself had one layer where they have cellulose and PCM pellets. Okay. So, in the next one what I am going to show is passive versus non-passive thermal energy storage. So, in a non-passive what happens is we have a fan actually. So, here it was just the heat was coming through the walls, trying to get conducted through the walls, and it was absorbed by the phase change material. So, in this case what happens is they actually have pillars filled with PCM pellets, and so this is for example the outside wall, then you have these pillars and then you have the inside the room. So, what they do is during the night time the cold air comes in and actually flows through the PCM, okay, and the warm air goes out during night, clear, and during the daytime the cool air comes in and goes out in this manner. Okay. So, this is the inside. So, what is happening over here is, let us just think about, this is a very nice artist rendition, I really like this picture and that is why I kept it here. So, it is warm air that is coming in, but remember in these pillars you have PCM pellets which are solidified, okay, which are already cooled. So, then what happens, through this the warm air goes in, and as it goes in the PCM gets melted, okay, and the warm air also loses heat, okay, and the air therefore cools down as it flows through these pillars filled with PCM pellets. These are porous material, and then or porous material, or maybe they flow from the outside, and then what happens is outside what comes out of these exhaust vents is actually cool air, all right. So, imagine a room wall with a series of these pillars filled with PCM pellets. So, as the air is pumped through, then what happens is it gives up its heat, the warm air gives up its heat to melt the PCM and comes out as cold air, which is used for air conditioning, clear. And the artist rendition also shows very nicely that at any point of time during the day what you will see is part of the, or whatever, certain fraction of the PCM pellets would be melted and some of it will still be in the solid phase. And then of course, as the day goes by, this boundary between gray and blue is going to shift from down to up, and hopefully by the end of the day, by the time the entire PCM has melted in all the columns, we already are in maybe during the evening time where the air conditioning load will come down, or the ambient temperature has also come down, right. So, this is another example. What I would say is PCM storage, sorry, why am I would use the same color material pen, PCM storage for building energy efficiency. So, again let us summarize what we discussed this time. We talked about latent thermal energy storage, and what we try to do here is, I mean look, we already the basic principle as to how this energy storage is taking place is known to us, we all understand that. So, what I tried to do here is I tried to show you 3 case studies, okay. The first one was using that solar where we were generating using solar energy to generate electricity, and what we were doing is on a sunny day and during daytime we were storing part of the solar energy was stored in molten salt, which was used during the time when solar energy was not available to us. In the second one, we used thermal energy storage to augment an air conditioning chiller unit, where we showed that part of the chilled water from a chiller plant was used to generate ice, and I said that this ice that is generated can augment the air conditioning load, or can help in meeting the peak air conditioning load during peak hours. Or I also gave you an example of a new company where they are trying to use this principle to provide air conditioning where there is power outage, or when there is power outage and the cost of generating electrical power or electrical energy using diesel gensets is very high, okay. And the third one was for building energy efficiency. I showed a case study in a little more detail where they actually in one case they put PCM pellets on the wall, okay, and what happened is the PCM absorbed heat during the daytime, okay, and preventing it from going into the inside of the room, and during night time it gave up the heat. And this is another example that was passive, and then there is also an active version of that where we can actually blow air using blowers over the PCM during daytime, so that it releases heat that goes to melting the PCM, and therefore, the air that comes out is cooled air used for air conditioning, and the vice versa happens during the night time. Okay. So, again when we actually melt the PCM and store energy, it is called charging, and when we actually and when we do the reverse, when we solidify the PCM and extract the energy out, it is called discharging. All right. So, I would just end this lecture with that on that note, and in the last two lectures what we have seen therefore is thermal energy storage, examples of thermal energy storage. The first one was sensible energy storage and the second was latent energy storage. Okay. Thank you very much.